All right, so writing the diagrams for the practice set for law sines and cosines is one of the most challenging parts. So let's look at a couple of these and see if we can draw a better picture. So in number 1, it says a plane flies 730 miles from Charleston, South Carolina to Cleveland, Ohio, with a bearing of north 30 degrees west. That means 30 degrees west of north. So I can imagine where Charleston is. It's over here, like on the east side. So I'm going to say that this is my start point. I'm going to label it Charleston. And what they're saying with the bearing north 30 degrees west is that we're traveling north, except that we're actually traveling 30 degrees west of north. So this is 30 degrees west of north. This is the actual flight path here. So this would be north. They're not traveling north, they're traveling 30 degrees west of north. So, and it says the plane flies 730 miles. So I'm going to continue this line, and it flies 730 miles. Okay, so this is where it flies. And it's Cleveland. Okay, so how about that? Does that make sense? Hopefully, because this is a video and you can't really answer me. Then the plane flies from Cleveland to Dallas, Texas at a south 42 degrees west bearing. So it's not flying south. It would be flying straight down if it was south. It's flying 42 degrees west of south. So this would be south. It's flying 42 degrees west of south. So this is 42 degrees. And it flies all the way to, oh, it says they're at the same latitude. So it flies, how far? It doesn't say. How far is Dallas from Charleston? So this is Dallas. And we want to know this distance. Question mark. So you have to take these different degrees, knowing that north and south are parallel lines. That will help you. That will give you angles. And if they're at the same latitude here, right, we've got a line that travels between Dallas and Charleston that says same latitude. So that will hopefully help you draw out number 1. The rest of the math you need to try for yourself, and then I'll help you draw out number 2. So number 2, Jack wants to build a tree house. His parents worry that he's building it too high. Unimportant sentence, but whatever. If Jack's dad is looking at the treehouse location from a 70-degree angle and then moves back 10 feet so he can see it at a 50-degree angle, how high is the treehouse's location? So first we need a treehouse. And then Jack's dad is looking at a 70-degree angle, so he's pretty close because he's looking up. So, dad, he's looking up at a 70-degree angle. I'm going to make the angle just from the ground though, because that makes more sense. And, whoops, my tape. Okay, so 70-degree angle. And then it says he moves back 10 feet. So we've got 10 feet here, 10 feet, and he's moved this way. And he's looking up. And now it's a 50-degree angle. So it's a 50-degree angle. So I really have this. So I've got 70 degrees here, and I've got 50 degrees here, and I've got 10 feet here. So what I'm looking for is the height of the treehouse. So I'm really looking for this angle. I mean, this height, not angle. and I want to calculate from there. So in a way, this is like our balloon problem example where we've got a triangle that's drawn, and then we have to draw that right angle for height as a secondary condition. So you'll have to use this triangle first, and then you'll have to use the information gathered from this triangle to figure out height. So you need to figure out the puzzle pieces and what you need to find first in order to do this problem. But this is an image of what can get you started. In number 3, you've got a picture, but maybe you want to draw it on your own paper. So a telephone pole is normally straight up and down, right? And now it leans 6 degrees from the vertical. So they're saying that it got hit over here with a car, and now it's this way, and that this degree right here is 6. A point 40 feet away from the base of the pole has an angle of elevation of 36 degrees. So we're going to go this way 40 feet, and then take our little measuring device where we can measure angles, and this angle to the top of where the pole is now, it didn't get taller, it's the same height, is 36 degrees. So that extra line in there, this one, that's what was perpendicular, but now the actual pole is this. So you want to use that in order to figure out all of your math. So it's kind of like number 1 in that sense. So the triangle disregards this, except that you need the 90-degree angle to figure out this entire angle. So then for number 6, they give you a picture, but you have to understand what they're asking. So Kristen's playing miniature golf. She hits the ball and it bounces off a brick. So it starts here and it goes this way and bounces off a brick at 110 degrees. And so it goes this way, and then it bounces and goes this way. And then they're able to calculate where if she'd have hit it straight, it would have gone that way. So this is the shortest path, is 8 feet. How far did the ball really travel? We need to add this side and this side. So we need to find the other 2 sides and add them together. So using the 8 feet and the other angles that we know, because they measured this angle, we can figure out stuff for number 6. Okay, so number 7, Janet is racing her friend Susan. So we've got these 2 chicks. They're starting here. We've got Janet and Susan. Susan runs 10 degrees away from Janet. So if Janet was running straight, then Susan runs 10 degrees away from her. So 10 degrees, that's not very much. Little tiny bit there, 10 degrees away from Janet for 2,000 feet. 2,000 feet. If she has to turn at a 50-degree angle to get back to Janet's path, how much shorter was Janet's run? So she's running this way, Susan is. Susan's on this side. Susan's running, and she would be going this way, but she turns 50 degrees. She turns 50 degrees, and this is the 50 degrees. This would be her path, the straight path, but this is 50 degrees. So here's her new path, and how much shorter was Janet's run? So then Janet's still running. I don't know who's faster. I don't know how this happens time-wise, but in order for them to meet at the same place, right, this has to keep going, and then this keeps going, and then eventually they meet and make a triangle. So you consider Susan is running on this sideways path, and she's facing this way, and then she turns 50 degrees. So getting the 50 degrees right here is kind of the issue. She would have traveled this path, but here's her turn 50 degrees. So this ends up being an obtuse angle. And that helps you see that she runs further, right? Because Janet's running the straight path and Susan's running further. And then you've got to figure out different things, because you have to figure out Janet's path so that you can compare Susan's path. So you have to find the other two sides and then compare them that way. So here it is a little bit closer up. This is Janet's path, and there's the finish. And then Susan's path is here and here. And they meet up at the finish line. All right, so that's me trying to help you with some of your sketches. And then the math you can do from there, law of sines or law of cosines. And thanks a lot. See you next time.